Welcome to this board exam review session. I am James Bolo, and today we are looking at sanitary engineering through the lens of JCB EduBuild Solutions. An excreta drainage system is a highly volatile pneumatic and hydraulic environment. Fluid and waste move continuously under variable pressures, exerting constant mechanical stress on every joint and fitting. Ignoring these physical realities leads to structural degradation. When a system fails, it bypasses the building's sanitation barriers, introducing severe biological hazards directly into occupied spaces. To truly master the National Plumbing Code, we have to look at how it governs this exact environment. We will deconstruct the code by tracing the precise pathway of effluent, starting from a single upper floor fixture and following gravity down to the city sewer. Every role in the code exists to manage exact thresholds of load, gravity, and maintenance access. For professional licensing, you must memorize these precise parameters. Understanding plumbing design requires eliminating guesswork. You must be able to strictly translate fluid dynamics into codified numerical values. Our pathway begins at the highest elevation, an upper floor bathroom containing a standard water closet and a lavatory wash basin. Before sizing any pipe, we must calculate the volume of waste entering the system. The code uses drainage fixture units, or DFUs, as the standard metric to translate fixture water volume into required pipe diameters. This table details minimum trap diameters and fixture unit values. Item 29, a private water closet, generates 4 DFUs with a 76 mm trap. Item 28, a single wash basin, adds 1 DFU and a 32 mm trap, giving our bathroom a cumulative load of 5 DFUs. This calculated load strictly dictates the minimum internal diameter of the vertical drainage stack needed to accept the combined waste without backing up. With the load calculated, we must select the correct pipe material. Cast iron and PVC are standard choices for vertical stacks, but the code imposes strict environmental prohibitions on certain materials. Reading Section 701.2.1, galvanized iron or steel pipe is forbidden underground and must be kept 152 mm above ground to prevent corrosion. Section 701.2.3 restricts vitrified clay pipes, which cannot be used above ground or when piping is pressurized. Once the approved material is selected, its smooth interior waterway serves a critical function. It minimizes frictional losses, allowing the effluent to accelerate efficiently as it drops down the vertical stack. The viability of the entire downward network relies completely on this initial step. Correctly matching the calculated DFU load with a material rated for the exact environmental stress of its location. Gravity handles the vertical descent, but eventually the stack turns horizontally to cross a lower ceiling plenum. Horizontal pipes are never installed perfectly flat. They rely on self-cleansing velocity, a flow rate fast enough to carry solid waste along with a liquid, preventing sediment accumulation. Section 302 mandates horizontal drainage pipes run at a uniform slope of not less than 20 mm per meter, or a 2% grade. As an exception, structurally constrained pipes 102 mm or larger may use a 1% slope with administrative authority approval. Maintaining velocity also depends on the geometry of the pipe joints. Because of this, horizontal connections require fittings of longer sweeps. Forcing horizontal flow through an improper 90-degree T causes immediate turbulence and blockages. Maintaining gravitational velocity is a fragile balance. Using the incorrect slope or the wrong geometric fitting instantly destroys the pipe's self-cleansing nature, leading to terminal system failure. Continuing our descent, the pathway reaches a mid-level floor housing a communal laundry room where multiple washing machines discharge into the main stack. Washing machines generate high volumes of suds, creating an expanding pneumatic pressure that can easily back up against gravity and blow out lower-level trap seals. Section 710 specifically addresses this suds relief. It dictates that fixture outlets shall not be connected to the horizontal drainage system within 2.4 meters of any vertical to horizontal change of direction for stacks containing suds-producing fixtures. Past the sud zone, the main building drain drops towards the lowest basement level, approaching its final exit point to the city sewer. When fixtures are located in deep basements, below the crown level of the main public sewer, gravity is no longer an option. The waste must discharge into a watertight sump and be lifted mechanically. The code requires these mechanical ejector pumps to meet specific dimensional criteria. The minimum size of any pump discharge from a sump connected to a water closet cannot be less than 50.8 millimeters in diameter. Finally, the code admits an engineering reality. Despite perfect slopes and precise diameters, blockages will eventually occur. Therefore, it mandates strategic maintenance access points, known as cleanouts. Looking at Section 706.7, cleanouts must be readily accessible. For piping 51 millimeters or less, there must be a clearance of 305 millimeters in front of the cleanout. For pipes larger than 51 millimeters, the required clearance increases to 0.45 meters. A compliant engineering design assumes inevitable failure. Specialized rules for SUD zones, precise pump sizing, and mandatory cleanout clearances act as engineered safety valves to mitigate disasters. Zooming out to the holistic network, we see how all these isolated rules work simultaneously. The DFU loads, the slope percentages, and the safety clearances map perfectly onto the building's geometry. A compliant excreta drainage system relies entirely on this perfectly tuned triad: calculated load capacity, controlled flow velocity, and engineered physical safety. Mastery of these specific numerical constraints represents the absolute baseline expectation for achieving your professional license. Behind the dry tables and the code sections lies a fundamental duty. The engineer's responsibility is to protect public health by securely isolating and transporting toxic biological waste away from human populations. Keep these exact numbers locked in your memory. On behalf of myself, James Bolo, and the JCB EduBuild Solutions team, I wish you success on your upcoming board examinations. True engineering intuition requires visualizing this invisible mathematical framework behind every wall. Good luck and keep studying the code.